Hello there. My goal with this video is to show you how you can apply second-order differential equations to the motions of planets around the Sun. I have included a list of my sources at the end of this presentation. I will break this goal down into two parts. Goal 1. I will show you how to derive the polar function of a planet's orbit using differential equations. Goal 2. Using this polar function, I'll then show you how I simulated the 8 planets' orbits around the Sun. I recommend pausing the video on each slide to fully understand the steps I take to apply second-order differential equations to this type of motion and how I will go about simulating the planet's orbits. We can use differential equations to model systems of the motion of an object acting under a central force, which we'll call f of r. Some of these systems of motion are special cases, where f of r is subject to the inverse square law. You may recognize that gravity is one such force, as described by Newtonian physics. We'll use Trench's textbook on differential equations to set up our second-order differential equation and its solution, which we will be using in this video. Check out section 6.4 of Trench's textbook for more. To be brief, we'll be using a definition, U, to aid in computing the special case of the inverse square law, resulting in a second-order differential equation, which we will call big F of r, which is equal to the second derivative of U with respect to theta, plus the quantity U, which is also equal to some constant k over h squared. As big F of r models a type of periodic motion, it is useful to write it in amplitude phase form, where its phase shift, the quantity theta minus phi, will be referred to as some particular angle theta sub p for the remainder of this presentation. Additionally, as big F of r is a non-homogeneous second-order differential equation, we will need the particular solution in order to find the general solution, which we will then convert to polar form. In this case, the general solution of big F of r is u equals a times the cosine of some particular angle theta sub p plus the quantity k over h squared. Using the definition of u from earlier, we can rewrite the polar function in terms of r. We will want to simplify this polar function in order to match the form of Kepler's orbital equation. To do this, we will be using the definitions of two parameters, ρ, which is the semi-parameter of a planet's elliptical orbit, and epsilon, which is the eccentricity of that planet's orbit. You can derive the former following the steps shown here. The polar function's final form is r equals ρ over the quantity 1 plus epsilon times the cosine of some particular angle theta sub p, where if epsilon is between 0 and 1, then the orbital path described by this function is an ellipse. To recap, we started with a non-homogeneous second-order differential equation, which we called big F of r, and then found the amplitude phase form of that equation's general solution. Then we converted that solution to the polar form of a planet's orbit, which we can use in DESMOS to simulate the planet's orbits around the Sun. I've compiled each planet's orbit's eccentricity value, epsilon, and semi-major axes, alpha, from orbital mechanics and astrodynamics. And prior to recording, I derived each planet's orbit's semi-parameter, ρ. Using this data, we can attempt to simulate each planet's orbit around the Sun. I will end the video with the DESMOS simulation, but before that, I wanted to make note of how I fared with goal number 2. Unfortunately, DESMOS is not equipped to solve second-order differential equations, and so I had to approximate the motion of a planet around the Sun. Namely, I used each planet's orbital time period and angular frequency to simulate the orbital speed of each planet compared to the others, as well as the planet's angular momentum at aphelion and perihelion, the farthest and closest distance to the Sun, respectively. To see how this was done exactly, take a look at the back of house folders in the DESMOS graph. Thank you for watching, and enjoy the simulation.